right? Assume there is a uniform disk, okay, of mass m, radius r. The disk is placed vertically and it is pivoted exactly at its center. So one of you tell me, if we just leave the disk like this, will it start rotating? The disk is pivoted exactly at the center. If we leave it like this, will it start rotating on its own?
No, sir.
Obviously it will not. What forces act on the disk? It's placed vertically and it is pivoted exactly at the center.
Gravitational force.
The only force, okay. One of the forces is gravitational force. The other force is the force exerted by the pivot. They'll balance. Net force 0, net torque 0. Gravity acts through the center of mass, center of gravity actually, center of mass. And the pivot is also exactly at the center of mass. So their lines of action pass through the axis. Net force is 0, net torque is 0. It will continue to be in equilibrium. Okay. But assume a particle is attached to this disk. Okay. The particle's mass is m by 2. It is attached exactly on the circumference of the disk. Now you tell me, if we release this disk plus particle system, will it rotate or will it stay like this itself?
It will rotate.
It will rotate because there is some extra weight on one side. Okay, so this system cannot be balanced. Rishi, are you getting it? No response. Okay. See, this is not a balanced system. There's some extra weight on one side, so it will definitely rotate. That particle will come down. Okay, as the particle comes down, the disk also rotates. Okay, so system is released from rest. Derive its angular acceleration alpha just after it is released. Derive alpha just after it is released. So it's a disk plus particle system. Particle is rigidly attached to the disk. Try. I'll give you all 2 minutes. Quickly visualize the forces acting on the disk and the particle along with their lines of action. Okay. Then you know that the disk is pivoted at the center. So the disk plus particle can rotate about that axis only. So about that axis, write net torque, equate it to I alpha, you will get alpha from there. Make it fast. I got one answer as 2g by 3r. I don't think that is correct. I think you made a mistake in calculation of moment of inertia. Check that once. Okay, let's discuss. Pawan, tell me what forces act on the disk and the particle. Disk we had already discussed. The weight of the disk will be acting. And the force exerted by the pivot, we don't know in which direction it acts. So I'll consider it in a random direction. Somewhat like this. Okay. And the particle's own weight also will be acting. And it acts here. That is mg by 2 because its mass is m by 2. Okay, these are the forces that act on the system. Now we want the angular acceleration alpha just after it is released. So you need to write tau net is equal to I alpha, and it's restricted to rotate about a particular axis. So we need to find out net torque about that axis. Okay. Rishi, can you tell me which of these forces creates a torque about that axis?
Or mg by 2.
Only the weight of the particle. See, there will also be a force between the particle and the disk. Okay, particle is attached to the disk. No, they are stuck to each other. So some force will be there between them, but that will be an internal force to this system. That the torque produced by it also will be internal torque. Net, it won't contribute to net torque. Okay, so the only force which produces torque is mg/2 because its line of action does not pass through the axis. Okay, and to calculate torque, we need the perpendicular distance from the axis to the line of action. This is r itself. Therefore, net torque on this system is mgr/2. Fine. Now we need to just equate this to I of the system multiplied with alpha, and we have to take I about the same axis about which we calculated torque. Vanilla, you tell me, how much is the moment of inertia of this system about the axis, given axis?
mr square by 2, sir.
Whose moment of inertia is mr square by 2? Whole system.
Sir, m plus m by 2 into r square by 2.
Okay, you can't just combine m/2 into the mass of the disk. Okay, disk mass is spread over the entire area. Particle mass is only at one point. No, so you can't say total. You can't take all the mass together and write 3m/2 into r square by 2. No, the total moment of inertia of this system. Okay, anybody else? Would you like to tell how much the moment of inertia of this system will be? Okay, this system is a combination of a disk and a particle. No, so total moment of inertia will be moment of inertia of the disk plus the moment of inertia of the particle. You have to write it separately. For the disk, it is the own axis of the disk, so mr square by 2, and particle's mass is m/2. It is at a distance r from the axis. What is the moment of, how do you express the moment of inertia of a particle? Mass multiplied with square of distance. The mass is m/2, distance is r, and you square it, it becomes mr square by 2 again. So this is the total moment of inertia of the system multiplied with alpha. That's all. So, okay, I think after this you can solve. That is how you find out the angular acceleration alpha of this system. So if you are given a combination of systems like this, like moment of inertia will be the sum of moments of inertia of individual systems. Rishi, where were you stuck? Why were you not able to answer this problem?
Torque calculation, I keep getting confused for every question.
Like, what exactly are you not able to understand or recollect?
Sometimes it's just the calculation errors I make, but I'm able to understand them.
Okay, okay, fine. Pawan, what about you? Where were you stuck?
Sir, moment of inertia देखो.
Okay, okay. See, you can identify where you are lagging, no? Not just in this class. Generally, when you're solving problems also, if you identify where you're lagging, work more on that. Spend some time on that topic till you become comfortable. Okay, next. Fine, let's consider a disk itself. Assume this is a pulley. Of mass m, radius r. Okay. See, till now in laws of motion and work energy power, we never considered pulleys that had mass. Okay, but now we can. Suppose there's a pulley, okay, attached to the ceiling, and you can see it is pivoted at the center itself. The support is connected to the pulley at the center. Assume there is a string wound around the pulley, and okay, it is wound tightly around the pulley, and one end of the string is open and a block is connected to that end. Okay. Assume the block's mass is m. Pulley's mass is m, radius is r. Consider the pulley as a disk. See, not every pulley is shaped exactly like a disk. You will be given in the question, okay, how exactly you need to consider it. For this problem, I'm asking you to consider it as a disk. Can one of you tell me what will happen after this system is released from rest?
So the block M will accelerate.
M will accelerate downward. What about the pulley? Pawan, what do you think will happen after this system is released?
సార్ పుల్లి రొటేట్ అవుతూ ఉంటుంది ఇంకా బ్లాక్ యాక్సిలేషన్ వస్తుంది.
Pulley will be rotating and the block accelerates downwards. Correct. So system is released. Find out. Okay, I'll tell you all the steps. First step you need to do, indicate all forces. Start doing this, all of you. Draw the system roughly and start doing this. Indicate all forces, then see the block will simply accelerate downwards, you know that. So one of you tell me, what kind of motion does the block execute? Like we discussed two types of motions till now, translation, rotation. What kind of motion does the block execute?
Translation.
Translation, why will it rotate? The string is passing through its center. Okay. So block executes translation. So write F net equal to MA for the block. What kind of motion does the pulley execute?
Rotational motion.
Pure rotation. So it will have some angular acceleration alpha. You look at all the forces that act on it and then write this equation. Tau net equal to I alpha for the pulley. Okay, do this fast, all of you. And after this, I'll tell you how to solve the equations and actually find out A and alpha. Okay, Pawan, tell me what all forces act on the block?
సార్ గ్రావిటేషనల్ ఫోర్స్ అండ్ టెన్షన్ ఫోర్స్.
Okay, so its weight mg will be acting and tension will be acting. Fine. So tell me Newton's second law equation also, Pawan, for the block. We are assuming it accelerates downwards. So according to that, how will you write the equation?
mg minus t is equals to ma.
Mg minus t is equal to ma. Okay. In this equation, tension is unknown and acceleration of the block is also unknown. Fine. Vanilla, tell me what all forces act on the disk pulley.
So tension and the force exerted by the fluid.
Okay. Tension will act here. Same amount of tension. Assume string is ideal. Okay. Pulley is non-ideal. It has mass. String, let us still assume it does not have mass. Okay. Tension and what did you say?
Force exerted by the pivot.
Force exerted by the pivot. Okay. We don't know the exact direction in which it acts. So let's consider a random direction like this. Is that all? The pulley has mass. Okay. So its own weight also will be acting. Okay. Now you can see the lines of action of the forces. So Vanilla, tell me which of these forces creates torque on the pulley?
Tension.
How much torque does it create? Or wait, Rishi, you tell. You can see the line of action of tension. We don't know the magnitude exactly. Keep it as T itself. How will you express the torque created by tension on the disk? See, torque is magnitude of force multiplied with the perpendicular distance between the axis and the line of action of the force. The pulley is restricted to rotate about this axis. Okay, so from there to the line of action of the force, the distance, the perpendicular distance is simply the radius. Therefore, the torque here becomes T multiplied with R. That's all. mg, the own weight of the pulley, and force exerted by the pivot cannot create a torque on it because their lines of action pass through the center of mass. Okay, or axis, not center of mass. So this should be equal to moment of inertia of the disk. Okay, pulley is supposed to be assumed as a disk in this problem. So mr square by 2 multiplied with alpha. And again, in this equation, tension is unknown, alpha is another unknown. So totally we have 3 unknowns. Okay, but only 2 equations. One is the force equation for the block, the other is the rotation or the torque equation for the pulley. Okay, you all think about this first. If we don't allow the block to move, suppose we hold the block, will the pulley rotate?
No, sir.
No. Okay. If the block goes down slowly, will the pulley rotate slowly or not? Pawan, you tell me.
Yes.
Definitely. And if the block moves faster, the pulley also will have to rotate faster. So their motions are linked to each other. There is a restriction in how they move. Okay. Suppose you don't allow the disk to rotate, the block cannot go down. Okay. So there is a constraint here. The acceleration of the block should be related to rotation of the disk or the pulley. Okay, we need to derive that relation now. Observe carefully. The only thing connecting the block and the pulley is the string. Okay, so we must use the string constraint here. Now, one end of the string is connected to the block at this point. Let's call this point as X. We don't know where exactly the other end of the string is. It is wound around the pulley a number of times. See, actually the system is like this. If any of you are facing difficulty visualizing, you can think of it as a spool of thread like this, and assume like some thread is loose on one side and a block is connected here. Okay, that is how it is. You are looking at it from the side. Okay, so fine. So we don't know where the other end of the thread is or the string is, but we can see that this point of the string, okay, you call it as Y, is about to lose contact with the disk, okay, or is about to get unwound from the disk. Are you all able to visualize this? As the block goes down, that particle of the string Y is about to lose contact with the disk. Okay. Now the distance between X and Y cannot change because that part of the string is straight. So whatever is the acceleration of X, same should be the acceleration of Y. That means this point of the disk should have a tangential acceleration equal to the acceleration of the block. Is this point clear to all of you? Any doubts in this? The point of the disk where the string is about to lose contact should have the same acceleration as the block. Okay, and the string there is in the tangential direction, no? So the tangential acceleration of that particle of the disk should be equal to the acceleration of the block. That is the constraint. Rishi and Pawan, did you understand?
Yes.
Yes.
Okay. But still, we seem to have introduced another unknown, tangential acceleration and acceleration of this thing, block. They are equal. How does it help us solve any equations? Can any of you tell me, in circular motion, what is the formula for tangential acceleration?
R alpha, sir.
R alpha, correct. That particle of the disk where the string is about to lose contact is at a distance r from the center. Therefore, the tangential acceleration there can be considered as R alpha. Therefore, A is equal to R alpha. This is the third equation for us. Now we have three equations and three unknowns: tension, acceleration A, and angular acceleration alpha. And we'll be able to solve them. Okay, so let me do this quickly. I'll solve this one, you solve the next. A is equal to R alpha. So in this second equation, if you cancel R, one R and one alpha will be left on the right hand side, will be remaining on the right hand side. That R alpha can be taken as A. Therefore, you get tension is equal to MA by 2. If tension is MA by 2, substitute that here and send it that side, it effectively becomes mg is equal to MA plus MA by 2. That is 3MA by 2. G gets cancelled. Okay, wait. M gets cancelled. And you will be left with acceleration is equal to 2G by 3. Okay. So the acceleration of the block in the downward direction is 2G by 3. And you know A is equal to R alpha. So alpha is equal to A by R. Therefore, the angular acceleration of the disk becomes 2G by 3 R. A divided by R. Is the solution clear to all of you? We'll solve another problem like this. If you have any doubts, you can ask. Okay. Fine, forces and all will be the same anyway, but we are going to introduce an extra block. Okay, there is some concept also that you need to understand before you start solving this. Suppose this time there are two blocks connected like this. In both blocks, tension will be acting through the midpoint, so blocks won't rotate. Okay. Assume the blocks are not of equal mass. Right side block, let it be M itself. Left side will take a smaller block this time. Or let's call this as M and that one as 2M. Disk, let it be mass M, radius R. Okay. Think carefully and answer. The string is ideal, okay, meaning it is massless. Massless, inextensible also. Let's say the string just passes over the pulley. It's not wound around the pulley, it just passes over it. Okay. Fine. So only on the upper side there is string, and then on the sides. If the pulley is smooth, if pulley is frictionless, tell me what would happen after releasing this system.
The pulley will rotate and 2M will fall down.
Okay, pulley will rotate, 2M goes down and M goes up is what you are saying. Fine. Any other ideas, anyone? Pawan, what do you think will happen?
Sir, same.
Rishi?
Yeah, so that should only happen at the same time.
Sir, I think the pulley won't rotate.
Correct. The pulley will
Sir,
not. Huh.
it'll rotate to a while, but it won't go back again because the mass is 2m, right? It'll
Let it
come
not go
towards the
back.
right.
Will it rotate or not? Like what happens just after it is released is what we want. What happens after a long time is not the discussion now. Okay. Vanilla, why do you think the pulley will not rotate?
Sir, the net torque is 0.
How do you say the net torque is 0? Oh, because there is T on this side, T on that side, net torque will be 0.
Yes, sir.
Okay, so what she's saying is one tension acts here, the same tension acts here also. If one tension tries to rotate it clockwise, the other tries to rotate it anti-clockwise, net torque should be 0. That is the idea that she is saying. Okay, we'll see, we'll discuss this in detail. So my question was, if the pulley is frictionless, what happens? And some of you said it rotates, some of you said it won't rotate. Pawan, can you tell why it rotates?
సార్ మాస్ 2m ఎక్కువ కాబట్టి ఆ ఎంఐని మాస్ తో కంపేర్ చేసుకుంటే ఇది ఎక్కువ.
Masses are not balanced. Okay. So system will not be balanced. That is also fine. So some disturbance should happen. What will make the pulley rotate is my question. What force makes it rotate, or what force produces torque on it? Do you think the tensions won't be same? See, if tensions are equal, one produces clockwise torque, the other produces anti-clockwise torque, net torque will become 0. If tensions are unequal, net torque on the pulley can be non-zero. So do you think they'll not be equal? Okay, fine. Rishi, what do you think? Or you said it will rotate. What will make the pulley rotate?
Because on the right side the mass is 2m. Because it's
Huh.
heavier on this side, it will obviously be unbalanced a little bit. And when this thing
So,
comes this side, there will be little movement.
so you're saying the tensions won't be equal.
But the mass is more, so
Mass is more. So will that make the tension on that side more? Okay, fine, fine. Actually, if the pulley is frictionless, it will not rotate. Okay. Tension will be equal on both sides and the pulley will not rotate. Okay, we'll discuss this in detail, but I want to ask you another question also before we proceed with the discussion. If the pulley is rough, then what will happen? The surface of the pulley is rough and the string is passing over the pulley, right? It is arranged over the pulley. Now, definitely 2m side will go down and m side will rise up. So the string has to move. String has to move like this. Okay. But the string will be pressing the pulley. And if it has to move against something which it is pressing and that surface is rough, then friction will come into play. So you all think and answer. What do you think will happen this time?
సార్ పుల్లి రఫ్గా ఉంది కాబట్టి ఆ స్ట్రింగ్ తో పాటు రొటేట్ అవుతుంది.
Okay, she's saying since the pulley is rough, it will have to rotate along with the string. one possibility. But Vanilla, you tell me, it's a light inextensible string. If the tension is T here and the tension is T here also, what produces a torque on the pulley then? Or do you think the tensions will be unequal this time?
ఫ్రిక్షన్ ఎక్కువ ఉంటే అన్ఈక్వల్ అవ్వచ్చు.
Okay, so due to friction, you are saying the tension may be unequal. Good. That is correct only actually. See, we'll discuss both cases now. First, assume the pulley is frictionless. So a thread is simply passing over this pulley. Now 2m side, due to gravity, it will have a tendency to go down. M side also has a tendency to go down, but 2m side gravity is stronger. Okay, so 2m has to go down, m has to rise up. The string has to slide over the pulley like this. One side, the length of the string has to decrease, the other side it will have to increase. So the string will have to slide over the pulley. And if the pulley is frictionless, no, the string can freely slide. Okay, so even if the pulley has mass, it has moment of inertia, still it doesn't matter. Okay, it is like like those regular laws of motion problems that we used to solve. Okay, so you can apply Newton's second law for 2m, Newton's second law for m, then constraint relation, their accelerations are equal, you can solve. In this case, if there's no friction, no, tension will be same everywhere. Why will tension be same everywhere? Because it's a massless string. Okay, in a massless string, tension has to be same everywhere. There is no other force acting on the string. Okay, so tension has to be same everywhere. So if the pulley is frictionless, what happens is this: 2m goes down with an acceleration a, m goes up with the same acceleration a, that's the constraint, and tension here will be same as tension here. And the same tensions will act on the blocks as well. So for the block, you will write 2mg minus t is equal to 2ma. For the other block, you will write t minus mg is equal to ma. Solve these equations, you will be able to find out acceleration and tension. Okay, but if the pulley is rough, and suppose you are told that the string does not slide over the pulley. Does not slide means what? As Vanilla was saying, when the string moves over the pulley will have to rotate along with the string. Okay, so let me adjust the diagram a little bit. Just a moment. Let's consider thick rope so that you'll be able to visualize better. Okay, the situation is somewhat like this. Fine. So particles of the string are in contact with particles of the pulley. So when the string tries to slide over the pulley, there will be friction generated between them. So let's highlight one particle of the string. Okay, let's say this. Okay, I don't think you'll be able to see it. Okay, take this particle in red. It's a particle of the string, and just below it, take one particle on the pulley or the disc. The red particle and the green particle, they are in contact with each other. You can visualize some more like that. Okay. All these particles of the string, they are in contact with particles of the disc. So as the string tries to slide over the pulley, what happens is these red particles and the green particles which are in contact have to move together. There should be no relative sliding. We are assuming that friction is sufficient. Okay, they'll mention that in the question. friction is sufficient to prevent slipping between the string and the pulley. Okay, or they'll just write string does not slide over the pulley. String does not slide over the pulley doesn't mean string won't move at all. Okay, string will move, pulley will rotate along with it. Okay, relative sliding will not be there. That is what they mean by it. Okay. So due to friction, what will happen? See, had there been no friction, the string particles would have slid clockwise. Okay, because 2m is on the right side, the heavier block is on the right side. So string particles have a tendency to move like this or to rotate like this. Now friction will try to prevent sliding between the pulley and the string. So what friction will do is, on the string particles, it will act tangentially backward. See, understanding this is important. On every element of the string which has a tendency to slide over the pulley, there will be small amounts of friction acting like this. And there will also be small amounts of friction acting on the corresponding particles of the disc or the pulley, like this. That is what makes the pulley rotate. Okay, now we don't know how much friction acts between them. We don't know the exact expression. Okay, that is difficult to derive also, but there's one thing we can do. At the right end of the string, or this point, okay, let me take a darker shade. At this point, there will be tension acting along the string like this. On the other side also, there will be tension acting along the string like this. Now, usually in a massless string, the tension is same everywhere. But in a massless string also, if extra forces act in between, then tension can change from point to point. So what I'm saying is, assume this is the string. It's a light inextensible string. Light means mass tending to 0. If mass tends to 0, net force should be tending to 0. Net force on the system, on that object should be tending to 0. So net force on the string must be 0. That's okay. Let's say at one end of the string, you are pulling with a force F. Now to keep it in equilibrium, or for the net force to be 0 on it, one choice is to exert another force F here. In that case, what will happen? Tension everywhere will be the same and it will be equal to F. But to make the net force 0, there are other ways also. You apply F by 2 here and another F by 2 at the midpoint of the string. Now also the net force is 0. Okay, but observe the tension this time. You consider any one section here. Let's take a random point of the string. Consider this part. Now this right side part of the string, which I'm highlighting, has to be in equilibrium. What force is acting on one end? F is acting. The other side, the only thing that can keep it in equilibrium is the tension there. Tension developed within this string. Therefore, for this part, this yellow shaded part to be in equilibrium, tension should be equal to F. Therefore, the tension everywhere in this region is equal to F. That's fine. Now you consider one point of the string somewhere here and take this part of the string. This part is also massless, means net force on it should be 0. On one end you have F by 2, means on the other side there should be a tension equal to F by 2 acting, okay, to keep it in equilibrium. Therefore, tension everywhere in this half of the string or rod, whatever it is only F by 2. So in a massless object, okay, in a massless string or a massless rod, the tension need not always be the same everywhere. If additional forces act in between, tension can be different at different points. Okay, and see what is happening. One strong force F is acting on one side, two weaker forces are acting on the other side, opposite direction. Okay, where the strong force is acting, tension is high. And where the weaker forces are acting, tension is low. Is this clear to all of you? That tension on a massless string in a massless string need not be same everywhere. Did you understand this point? Vanilla, is this clear?
Yes, sir.
Pawan?
Yes, sir.
Huh. So if additional forces act in between, a string can have different tensions at different points, even if it is massless. Now see what is happening here. On the string, small friction forces are acting. On every element they are acting. Okay. And we know that from everyday experience, we know that this system is going to go down on the side of 2m. The pulley is going to rotate clockwise. If the pulley has to rotate clockwise, this tension, call it T1, should be stronger than the other tension T2. Why should it be stronger? Because only if it is stronger, its torque will dominate the other torque, and the net torque will be clockwise. So from everyday experience, we can tell that T1 must be greater than T2. But how do we justify that? The string is massless. How can we say that it has different tensions at different points? Because there are additional forces acting in between. These small friction forces that are there. Since it's very small, I'll call it as dF. Okay, small amount of friction. They're acting everywhere, wherever the string is in contact with the pulley. Okay, so basically here what is happening, T1 is a strong force and there are many weaker forces, and T2 is also a weaker force on the other side. Okay, so as you go from that side to this side, the tension gradually decreases. Okay, when you move from right side of the string to the left side of the string, tension gradually decreases. Friction, because friction is acting in that direction from right side to left side. Okay, so T1 will be stronger tension than T2, and that is why the pulley rotates. Now pulley is actually rotating due to friction, correct? Now you come back to this diagram that we have drawn on the side. One force we have applied is F on one side. Okay, let me just change these forces just to make the idea clear. Let's take on the other sides, let's take two forces. One as 3F by 4 and this as F by 4. Okay, then the tension here, the balancing tension here will have to be 3F by 4. Okay. On one end, the force was F. Till the point where F by 4 acted, the tension was F everywhere. Where F by 4 acts, after that, the tension decreases to 3F by 4. Okay. In the right side part, tension is F. In the left side part, means once you cross the point where F by 4 is acting, tension decreases to 3F by 4. Okay, means this additional force that is acting in between is the same amount by which tension decreases. Are you all getting my point? Any doubt in this? When you go from one end of the string to the other end, whatever extra force acts in between, by that much amount, the tension will decrease whenever you cross that point. Okay. Now, in this problem, friction is what is making the pulley rotate. We don't know how much friction is acting on it, but there is something we can do. Imagine moving from this point of the string to the other side, to the left side. When you move from this point of the string to the left side, there are many points in between where frictions are acting. We don't know how much each of those frictions is. Okay, how much the magnitude of those frictional forces is. But using this logic, we can tell that for every dF, the tension decreases by the amount dF. Because in this example, in the right side case, when force F by 4 is acting, tension is decreasing by F by 4. So same thing should be happening with this string also. Whenever friction dF acts, okay, at whichever point friction dF acts, when you move across that point or when you pass through that point, tension should decrease by dF. So tension decreases by dF and all. So whatever is the sum of the frictions acting on each element of the string, that itself will be the change in tension from the right side to the left side. Okay, that is what I'm saying. So effectively, tension on the right side was T1, no? T1 minus summation of all the friction forces, okay, should be equal to T2. That is what I'm saying. Because as you move from the right end to the left end of the string, In between, there are some df forces acting. Whenever a force df acts, tension decreases by df. So how many ever dfs are there, tension decreases by those many dfs. So the same idea, I have put it mathematically like this. Tension on the right side minus summation of all the dfs must be equal to tension on the left side. Therefore, we can say that summation of all the small amounts of friction acting is equal to or will be equal to T1 minus T2. And this is what helps us express torque acting on the pulley. The pulley rotates due to friction. Okay. So torque on the pulley is the sum of all frictions acting multiplied with the radius, because they are all acting at a perpendicular distance r. But we don't know how much is each friction. And we don't know the sum of friction also, but we have a way to express that now. Net torque on the pulley can be written as T1 minus T2 into R. Okay. See, you might have learned this from your teachers or some books also, but they will directly tell you T1 minus T2 into R. But this is the reason. Okay. Actual force that makes the pulley rotate is friction. The friction can be expressed in terms of tensions. Okay. So the net torque produced by or the torque produced by friction on the pulley can be expressed as torque due to T1 minus torque due to T2. That is T1 into R minus T2 into R. That is T1 minus T2 into R. Okay, we are just looking at things in detail. Okay, fine. So I hope the situation is clear now. The tension will be non-uniform. One side of the string will be having one tension. In between, there are frictions acting. So tension will get disturbed. The other part of the string will have a different tension. But these same tensions will be acting on the blocks. So on 2M, there will be T1 acting like this. On M, there will be T2 acting like this. Because here there are no extra forces acting on the string. So in the vertical part of the string, tension will be same everywhere. So left side vertical part, tension is T2 everywhere. Right side vertical part, tension is T1 everywhere. On the part of the string which is passing over the pulley only, tension varies from point to point. Okay, now, I mean, solving is same as before. What you will have to do is apply Newton's second law in translation for the blocks and rotation for the pulley. Okay. Rishi, quickly tell me, assuming this block goes down with an acceleration A and this block goes up with an acceleration A and the pulley rotates with an angular acceleration alpha. Rishi, tell me Newton's second law or net force equation for 2M.
So F net is equal to MA.
I know. Go on.
Mass is, so it'll be 2M into A.
2M into A is the right hand side. How do you write the left hand side? F net. Pawan.
Sir, 2mg minus T1 is equals to 2ma.
Its weight 2mg minus the tension acting on it is T1 is equal to 2ma. What are the unknowns in this equation?
Sir, T1 and A.
T1 is unknown, A is unknown. Okay. Yusuf, can you tell F net equal to ma equation for the other block?
The M minus T2 is equal to,
Why are you saying mg minus T2? Why downward force minus upward force? Why not the other way?
so then T2 minus mg.
On what basis do you decide how exactly to write the equation? You decide it based on the direction of acceleration. Okay, acceleration of that block is upward. So upward force minus downward force is mass multiplied with acceleration. Okay, but here T2 is an unknown. So another unknown, we need one more equation. Another equation you can write is constraint A is equal to R alpha. But now alpha becomes another unknown. Okay, so we need a fourth equation now. That fourth equation will be the torque equation for the pulley. And net torque on the pulley, we have already written that T1 minus T2 into R. T1R torque is clockwise, T2R torque is anti-clockwise, but we know the pulley is going to rotate clockwise. So dominant torque T1R minus the weaker torque T2R is equal to I of the disc, okay, pulley or disc. I'm asking you to take it as a disc, okay? If they want you to consider it as something else, they will mention it in the question, or they will give you its moment of inertia directly so that you don't have to calculate. So let's write generally only moment of inertia of the pulley multiplied with alpha. So there are four unknowns now, T1, T2, A and alpha, and you will have 4 equations this time. Okay, solving you can do. Fine, let's quickly go through what we discussed till now. We just solved a few problems based on tau net is equal to I alpha. First was this system, a disk pivoted at the center with a particle attached to one side, on one side. So definitely there will be an imbalance. The particle will tend to move down. In the process, it rotates the disk also because it is rigidly attached to the disk. So in that case, we wrote tau net is equal to I alpha and derived the angular acceleration. Next is pulley with a string wound around it, and at the other end of the string, there was a block attached. Okay, something like this. So if you release this system, the block will go down, the pulley will rotate. We derived the acceleration of the block and angular acceleration of the pulley. Next question was an extension of that. Okay, string is on both sides. There are 2 blocks. Okay, but this situation is interesting. Till the last chapter, work energy power, we always assumed pulleys to be ideal. Ideal pulleys are frictionless pulleys. So string will simply slide over them or slip over them without rotating the pulley. But if the pulley is rough, and they mention that string does not slide over the pulley, it doesn't mean string doesn't move at all. String moves, the pulley rotates along with the string. Okay, so in that case, you will have to include the motion of the pulley in the equations. And if friction is acting on the string, okay, the part of the string which passes over the pulley, tension varies from point to point. So right end of the string will be at a different tension, left end of the string will be at a different tension, even though it is a massless string. Okay, fine, we'll stop it here for now. I have some urgent work. And as I said, you will be having another class tomorrow, most probably from same time, 7 to 8.